Welcome everybody to today's specific Quasiworld seminar. So we have only one speaker today, namely Krishnendu Gongopadhyay. I hope I didn't massacre this too badly.
No, perfect.
And
Yes.
he will talk about the combinatorial structure of symmetric classes in the modular group. So please.
Okay, so thanks to the organizer for inviting me to this beautiful seminar series, and I really appreciate for your cooperation to accommodate me today. My talk was supposed to happen last week, but because of some viral fever, I could not turn up. I was so tired and exhausted. But thanks to the organizer for giving me another opportunity to give this talk today. So I will give my talk shortly. But before that, I have one question. The talk is for around 50 minutes.
Yeah, 50 minutes. Plus
50 minutes. Okay,
plus
great.
questions.
Great. Yeah, great. So at the moment, I will write on my laptop, but my laptop is kind of, foldable. So if I fold it, I will turn upside down. So I will switch off my camera, and then I have already shared my screen. So just give me 1 minute. So, yeah. So you can see my screen, right?
Yes.
Yeah, you can see my screen. All right. So this, so if I am not audible or you don't see anything, just interrupt me and let me know.
Yeah, we can hear you well.
Pardon?
We can hear you well.
Okay, great. So the talk is about combinatorial structure of the symmetric. I should put some apostrophe here because this is not, I don't know whether it is a very standard terminology or not, but we want to club several special conjugacy classes in the modular group, and that's what we are calling symmetric classes. Now, I think everybody in this audience know what is a modular group and what are hyperbolic spaces, but nevertheless, I will start by recalling them. So for me, H2 is the hyperbolic plane, which is the complex upper half space. Okay, so this is x-axis and this is y-axis. Okay, so this is a complex upper half space, and you have a metric on the upper half space. So H2 equipped with this metric is a model for hyperbolic geometry. So that is hyperbolic plane, and the boundary of the hyperbolic plane can be identified with the extended real line. And we all know that if we can, apply a automorphism or Mobius transformation, we can identify it with the unit disk where geodesics are semicircles orthogonal to the boundary. So in this model, the geodesics are semicircles orthogonal to the boundary. And the orientation preserving isometry group of the hyperbolic plane is PSL2R, that is SL2R modulo plus minus identity. And SL2R is just a group of 2 by 2 matrices with real entries and determinant 1. All right. So this is the kind of setup that we begin with, and we are in this particular talk, we are interested in, so one thing I must say, that how the isometry looks like. So PSL2R can be identified with the Mobius transformation, preserving the circle. All right. So the group SL2R acts on the hyperbolic plane by Mobius transformations with real coefficients and represented by a matrix in SL2R. So this also gives you a double covering from SL2R to PSL2R. But whenever we refer to a Mobius transformation, we often lift it from here to this linear group and work with matrices, because over matrices we can have conjugacy invariants like trace and several powers of trace, etc. Okay, so now in this lecture we are interested in the group which is the modular group, which is PSL2Z. So the group of 2 by 2 matrices with integer coefficient, determinant 1, modulo plus minus identity. So this can be realized as a subgroup of PSL2R. In general, we are interested in other discrete group as well, but in this lecture probably I will mention only one of them, which are generalization of this modular group. Yeah. Now, one thing I just mentioned here, that the modular group is a beautiful group, and there are several aspects to modular group. People are still trying to understand different number theoretic aspects, but for us, from geometric perspective, modular group also has a beautiful combinatorial structure. So as a combinatorial group, you can identify it with pre-product of Z mod 2Z. So Z2 is Z mod 2Z, and Z3 is Z mod 3Z. Okay, and sorry. Okay, and this modular group is generated by, so when you consider modular group as Mobius transformations with integer coefficients, I mean, there are two special Mobius transformation. One is this translation, and other is this rotation, which generates the modular group. Okay, so we denote at the moment gamma to be PSL2Z. Okay. Now, as we all know that whenever I take an element, so classification of elements, so every element in the isometric group of the hyperbolic plane can have at most one fixed point inside the hyperbolic disk, or it can have at most one or two fixed points on the boundary. Based on that, we can classify elements in PSL2R as elliptic, parabolic, or hyperbolic. So elliptic, parabolic, hyperbolic. So elliptic means it has a fixed point inside the hyperbolic plane. Now equivalently, so gamma in gamma, or you can also, I mean, in particular, I take gamma in PSL2R at the moment. Okay, elliptic if and only if the trace of gamma is absolute value of the trace of gamma is less than 2. Parabolic if and only if trace of gamma is equal to 2, and hyperbolic if and only if trace of gamma is greater than 2. So up to conjugacy, elliptic elements are cosine theta, minus sine theta, cosine theta. Parabolic elements are translations, and hyperbolic elements are diagonals with eigenvalue, at least one eigenvalue greater than 1. So this is the trichotomy or the classification of elements, elliptic, parabolic, and hyperbolic, that that we will use. And here, if you take gamma as a matrix, if you take the matrix representative of gamma, then trace of gamma is A plus D. Mod of trace of gamma is A plus D, mod of A plus D, and that classifies the dynamics of these elements. Okay, so this is the kind of background that we start with. Now, the main object, the motivation, one of the motivation for this talk are special kind of geometrically, PSL2Z is a discrete group. It has a nice fundamental domain. We all know that. Okay. And there are 2 points on the fundamental domain. Okay. One is of order 2, one is of order 3. There are two vertices of the fundamental domain. Now, this vertex of represented by a point of order 2 is important. So,
just to interrupt, sorry to interrupt.
Pardon?
Shouldn't the point be I? The point of order 2?
Pi.
I, the imaginary unit. You draw it as the one of.
Oh, right. Yeah. So I think I should not write a axis here, right? That's what you're saying. Yeah. So I think this is the. Yeah. So yeah. So let me write down, draw the picture properly. Yeah. So I was just going a bit fast here, but let me try to draw the picture properly. So modular group has a fundamental domain, and so fundamental domain for PSL2Z. Okay, so there is this, we have this x-axis, this is 0, and we want to draw the fundamental domain. Like I have this point here, the symmetric points, and we have this geodesic. Okay, and this is the point I. So this is the fundamental domain. All right, and these 2 points are symmetric. You call them maybe rho and minus rho. Okay, and this is
minus rho bar. Right? Minus rho bar.
Pardon?
Minus rho bar. Minus rho bar.
Rho bar. Okay, right. Because if it is rho, then this is minus rho bar, right? Yeah. So essentially, what is this line? This is actually real part of Z is half, and this is real part of Z is minus half. All right. And what are these corners? This is half plus root 3 by 2 I, which is this point, and this is minus half plus root 3 by 2 I. So this is minus rho bar. Yeah. All right. So this is the fundamental domain for PSL2Z. So that means PSL2Z tessellates the whole hyperbolic plane by translating this domain in using its action on the upper plane. All right. And this fundamental domain is of importance because you can, I mean, H2 mod PSL2Z, that is essentially, if you take this fundamental domain and you identify like this, so that gives you the modular surface. So it's an orbifold with 2 cone points, one of order 2 and the other of order 3. That's what I was mentioning. So I hope it is clear now. Yeah. All right. Now, for us, this order 2 cone point is important because I think it's a general definition. You take any geodesic on a hyperbolic orbifold, it has to it should have a order 2 cone points like this. Now call this geodesic gamma. If this geodesic gamma is equivalent, if gamma is equivalent to gamma inverse, which is the inverse geodesic, then a geodesic gamma is called reciprocal. All right. So reciprocal geodesics. So you take any, take any Fuchsian group. I would not denote it by gamma, but maybe lambda with elements of order 2. Then reciprocal geodesics are those geodesics that passes through the order 2 cone point. Now, this is the geometry. So reciprocal geodesics appear in different contexts, but this also has a very much group theoretic interpretation. And that's what actually we started with. So we started with the group theoretic interpretation and then realized that they represent the reciprocal geodesics. So now what I do, I will take a slight digression and I will define it, this reciprocal, the group theoretic counterpart for reciprocal geodesic for arbitrary groups, because this is a very general definition and can be asked for any group. So let G be a group. So an element G in G is called reversible. They are also known as real if G is conjugate in G to G inverse. That means there exists H in G such that G inverse is H inverse. Now, if H can be taken such that it is of order 2, then G is called strongly reversible or strongly real. So in this case, you can write G as product of two involutions. So this is a if and only if. So strongly reversible, if and only if it is product of two involutions. So now a general open-ended problem to classify reversible and strongly reversible elements in a group G. G can be any group. So this is a general theme of research that appear in many branches of mathematics. So like there are algebraic representation theory. There people call them as real or strongly real. But when one looks into these objects from a dynamical or geometric viewpoint, they are called reversible or strongly reversible because of some motivation that I would not get into here. So now every strongly reversible element is reversible, but the converse is not always true. Okay, the converse is not always true. So now, in our case, these reciprocal element, you see they are passing through a order 2 point. So essentially, if you reflect along this geodesic vertical line, that maps, that conjugates gamma to gamma inverse. So these are the hyperbolic element representing these reciprocal geodesics are precisely the strongly reversible elements in this sense. All right. Now, this terminology reciprocal, I learned it from a paper by Peter Sarnak, and the name of the paper is also reciprocal geodesics. So there he called such elements reciprocal. So we are also calling it reciprocal, but actually strongly reversible is more common name for such elements. So now you take gamma arbitrary Fuchsian group, not gamma, I mean let's denote it by lambda because I have already denoted the modular group by gamma. Okay, so this is Fuchsian group. Okay, now one can show, I think this result must be known to expert, but one can prove it independently also. So then, so for example, I mean, in my paper with Debattam Das in New York Journal of Math, we have sketched a proof of this result. So let lambda be a Fuchsian group. So an element G in lambda is reversible if and only if it is strongly reversible. So, if you take any group, reversible means G inverse is conjugate to G. And strongly reversible means one can obtain one conjugator H, which is the involution. But for Fuchsian group, something more happens. Further, if an element H in lambda conjugates G to G inverse, then H must be of order 2. So this is what I interpreted by saying that all reciprocal geodesics must pass through this order 2 cone points. And the only possible strongly reversible element are either hyperbolic elements or the involutions. So if the element is not strongly reversible, if the element is not involution, then it has to be the hyperbolic element, and the axis of the hyperbolic element correspond to a reciprocal geodesic. Okay, so this is the kind of background that we will now work, and we will not talk about arbitrary Fuchsian group, but we will restrict our attention for the moment to gamma equal to PSL2Z. So is there any question so far? Okay, so let me now go to the case of modular group. Okay, so I take gamma to be PSL2Z, and by this I denote the conjugacy class of gamma. Okay, so that means this is the set of elements which are conjugate to gamma. Now, here are some terminology that I would like to mention. So, an element gamma is primitive if gamma is not gamma not delta n for delta in gamma. Okay, and so there are so one of the main motivation for this paper comes from this paper by Peter Sarnak that he called reciprocal geodesic. So there Sarnak discussed different types of these strongly reversible classes in the modular group, both inside the modular group and in the extended modular group. And then, so what Sarnak did, let me just briefly recall. So Sarnak start with modular group, So one thing I must say that I forgot to mention here, that when you take a Fuchsian group or say modular group, suppose you take a hyperbolic element gamma and you have gamma reciprocal. Then H gamma, okay, that is a infinite dihedral subgroup of gamma. So classifying these reciprocal geodesics or strongly reversible classes amounts to classifying infinite dihedral subgroups of gamma, and that is of importance for group theoretic, geometric, as well as number theoretic purposes. That's what Sarnak discussed in his paper, Reciprocal Geodesics. Now, in this paper, Sarnak introduced 3 involutions. So, Sarnak introduced 3 involutions. So the first involution we denote by phi of r. The second involution is phi of w, which is just you. Yeah, so what is w here? So w is this matrix of determinant -1. So this is not an element in PSL, but an element in the full group of isometries. Okay, and then there was another involution, that is gamma maps to conjugate of gamma inverse by W. So except phi of R, the other 2 involutions, they does not come from PSL to Z, but they come from the full group of isometries. But if you take this collection identity, phi of R, phi of W, and phi of A, then they forms a Klein's 4 group. And the idea is to look at the action of this Klein's 4 group on the set of all conjugacy classes. So for any subgroup H of K, you define phi of H to be the conjugacy classes in the, okay, so what Sarnak did, he took the primitive conjugacy classes, and then you look at those classes which are invariant under this subgroup of the Klein's 4 group. So in particular, if you take individual element, then the set of all primitive conjugacy classes is those invariant under the identity map. The reciprocal classes, I denote it like this, that is those invariant under the transformation phi of R, gamma goes to gamma inverse. That means this is precisely the classes which are conjugate to their inverses. And then you have 2 more classes, I, which are invariant under phi W, and ambiguous. which is phi of A. Now, this means reciprocal classes or strongly reversible classes. In modular group. This is called inert classes, and this is called ambiguous classes. Now, these inert and ambiguous classes, they are also somewhat like not the inert one, but at least the ambiguous classes. If you see this definition, gamma is still conjugate to gamma inverse if they belong to the ambiguous classes. But here the conjugation element is a orientation reversing element. So we are so the reciprocal classes are also kind of can contain in these classes. And the inner classes are those elements where gamma and the special conjugate of gamma, they belong to the same conjugacy class. So algebraically, that's what it means. And what Sarnak did, he took the primitive reciprocal geodesic on the modular surface, and then he counted these different classes and obtained asymptotic count of all these classes using the trace or the length of the geodesic as the parameter. All right. So Sarnak counted the following quantity. Actually, let me write down the quantity at least. So this quantity, this class. So pi of hx. This you defined it to be sum of all classes in pi of h such that trace of gamma is less or equal to x. So this is the asymptotic that Sarnak counted for all these different classes. I would not give all the asymptotics here, but in particular, for example, for the reciprocal class, Sarnak proved that this is 3 by 8x. For the inert class, Sarnak proved that this is x by 2 log x, and for the ambiguous class, he proved that this is 97 by 8 pi square s log x square. So this was Sarnak's result. Okay, so now here they are counting in terms of the length of the geodesic or the trace. Now, after this work, yeah, so using the same kind of count, I mean, using the same parameter, which is the trace of the element or length of the geodesics, this result, some of these results has been generalized. So Erlandson and Suto, they have counted reciprocal classes for hyperbolic orbifolds. Or you take any group, Hicksian group with a order 2 element and take the corresponding hyperbolic orbifold surface. So they have counted reciprocal geodesics. This function for all such groups. And in another direction, Parkkonen and Paula, they have also used certain thermodynamical approach to count the reciprocal and ambiguous classes for negatively curved Riemannian, I would say, orbifolds. Okay, so they have generalized some of this work. In particular, this count of ambiguous classes has slightly been improved by Parkkonen and Paula using so they have used certain thermodynamical framework or geometric framework to generalize this result. So this is what is known using traces of the elements or hyperbolic lengths. Okay, so I just summarize it here. Okay, so now what we are up to. So now what we will do, we will discuss combinatorial approach. Okay, so whatever the work I mentioned, as I have already seen, as I have already mentioned, they have used the length of the geodesics or equivalently the traces of the hyperbolic elements to obtain count of the special classes. Now, what we will do, we will use this combinatorial representation of the modular group and want to count these classes using word lengths. So now the motivation to see this came from a work by Basmajian and Suzivalli. So they have developed a direct combinatorial method for counting reciprocal geodesics by word lengths using the above pre-product structure. Okay, so what they obtained, so their result I just maybe I state. So theorem Basmazian Suziballi. So this is 20, I think 2020. Okay. Yeah. So what they do, so if you take gamma, the set of primitive reciprocal geodesic such that the word length is less or equal to 2t, then it is asymptotically 2 to the power t by 2. Now, I must mention here briefly what is the word length. So, you know, in combinatorial group theory, a word is called cyclically reduced if all its cyclically permutation remain reduced, and corresponding to every cyclically reduced word, you have the concept of a word length. So you write it in terms of so let me recall. So you take any cyclically reduced word, and then the length of the word is the number of generators in its reduced form. Okay, so this is true for any two free products. So you take any two group A and B and take a cyclically reduced word, then the length of the word, and if I take, say, A, in our case, A generated by one element, B generated by beta, so take A and B cyclic, then take the reduced form of a word, then the number of generators in its reduced form, inverses allowed, is the length of a word. Okay? Yeah. So now this is the result of Basmajian and Suziballi for reciprocal geodesics. Now then, following this work, Marmolejo, he generalized what he did. So he counted gamma primitive reciprocal geodesic such that 2t. So he counted this result for Hecke groups. Okay, and Hecke groups, which is gamma p, where p odd. Now with Debattam Das, we have, or extended, let's say that, we have extended the above results for all Hecke groups. But this is for reciprocal elements. But now I have already mentioned there are two more classes, inert and ambiguous classes. Quickly tell you our result for inert and ambiguous classes, which is a joint work with Debattam Das and Khushi. I will show you the results using some slide. Okay, so let me just share my screen again. All right, so this is the result of Basmajian and Suzivalli, the combinatorial counting that they obtained. So they actually, what they have done, so they developed a method where, you can express every word in the modular group as a string of two words, A and B, where A and B are generators of Z2 and Z3. And then they obtain certain normal form of this element. And using this normal form, they essentially counted these words. Now we want to generalize it, this asymptotic counting formula, for inert and ambiguous classes using word length in the modular group. Now for that, let's recall the setup. You take the set of all hyperbolic elements in the modular group, take the conjugacy classes of hyperbolic elements, and these special classes, inert and ambiguous classes that I already discussed a while ago. And then every AB word representative of the inert class of length 40 has this form where m is a positive integer and m divides t, okay, where alpha I is plus minus 1. All right. Now, that means gamma is a t by m fold repetition of the block mu and mu star, these two blocks. Now, using this normal form, we have been able to obtain this result that you take the inert classes, or also you can take primitive inert classes of word length at most 2t. Then asymptotically, the number of inert classes of word length at most 2t is this quantity, 2 to the power, you take the greatest integer less or equal to t by 2 divided by the same number plus 1. All right. So this paper is on the archive. And then we go on counting the ambiguous classes. So similarly, we developed a normal form for the ambiguous classes, which is like a palindrome in the modular group. And this word is symmetric about its center. Now, there are two cases. Either t can be even or t can be odd. And depending on that, the normal form changes. So then using this normal form, we count these classes again, and we obtained the asymptotic count for all ambiguous and primitive ambiguous classes of length at most 2t. So when t is even, and you take the word length 2t, when t even, this count is 3 times 2 to the power t by 2, and when t is odd, this is 5 over root 2 times 2 to the power t by 2. Okay, so this is another count that we have obtained. Now, if you summarize all these, then this is the combinatorial analog of Sarnak's result. So you have the count of reciprocal classes of length at most 2t. You have count of the inert classes of length at most 2t, and you have ambiguous classes of length at most 2t. So this gives you a complete combinatorial picture of Sarnak's result, completing the program that Basmajian and Suzivalli started with reciprocal classes, and then later we generalized it for Heke groups, and recently they have also uploaded a preprint for Heke group as well, extending Marvelous result for all P, and their approach is pretty independent of our approach. So these two different approaches essentially converge to the same result for reciprocal classes, but combinatorial counting of the inert and ambiguous classes, we are not aware of any result before this preprint with Khushi, Mishra, and Debattam Das. So this picture, this completes the picture of Sarnak's counting for the modular group. And yeah, I think these are the references that I mentioned at different times. Yeah, so this is the paper from Basmajian and Sujivarli is a paper from 2022. And yeah, so these are the references that I mentioned. And yeah, these are the other two. So this paper by Parkkonen and Paula is now accepted, and you can see the precise reference on Paula's webpage. Okay, and our paper with this paper is available on arXiv with Khushi and Debattam, where these results have been proved in detail. Yeah, so with this, I would like to thank you for your attention, and I stop here.
Thank you very much. Let's thank our speaker. And let me start the discussion. So are there comments or questions? I mean, one question that I have, can you go back to the geometric interpretation of these different types of geodesic classes? So you said that for the modular group, these reciprocal geodesics are those that pass through the points of order 2 and are kind of symmetric with respect to the involution at these points? So,
right. Yes.
So what about these other classes? I mean, these inert and ambiguous classes?
Yeah. So, so they actually also corresponds to, they should correspond to reciprocal geodesics, but here the reciprocity is not, I mean, their orientation reversing involutions are also allowed. Okay. So when I am taking reflection here, passing through order 2 point, then reciprocal means the reflection has to be in a modular group. But in the extended modular group, when they can be this represented by this matrix 0, 1, 0. Yeah, this matrix.
I see.
0, 0, -1. But the other two classes are of importance, not because of geometric reason, but they also have certain connections with Gauss's ambiguous form.
Yeah, this was actually my second question, right? I mean, this terminology, I mean, this reminds me of classification of quadratic forms, right? So
yeah, exactly. So it is actually related to that. And Sarnak actually gave a detailed interpretation of how they are related. And this ambiguous class are precisely correspond to the ambiguous quadratic forms.
I see. Okay, thank you. So are there other
group theoretically, for me, group theoretically, they are all strongly reversible element. The reciprocal classes are strongly reversible element in the modular group, and the other two classes are strongly reversible in the full group of isometries.